remember, because any problem you handle you have with noise, there's usually a loop somewhere where current is flowing that shouldn't be there. You look where it's coming from, you see whether you could short circuit it to get a shorter wave, and then you can remove it from the other part of the system. That's what you do with current. And you can check, well, tip of the radio, that it works. And then next you reduce both loop areas, actually this one and this one. So this should be together, this should be. Well, this is, again, this same circuit. This is the noise from the outside world. And sometimes that could be a high value. Say a lightning, you got maybe 1,000 amps. Maybe a side track here, but sometimes you get these protection plugs here, you know, where you have a voltage protection against over voltages. You put one here, you put one here, and you still have the 1,000 amps. So it doesn't protect against this current. This is a difference in mode. If you have protection circuit here, there's a difference in mode protection. Not a common mode protection. It doesn't protect against this current. So if you want to protect against this current, it's probably better to put this plug in here together. That's the low frequency approach, but for lighting that's okay. Not be able to flow through your system. Okay. So this is the way to do it on a real circuit. You have a box with some electronics in it. You make a connector plate or gland plate, whatever you use, and you make sure that all your connections are on this plate, go through this plate. If it's a shielded wire, you can connect the shield to this plate. The plate will then function as a short circuit. If it's not a shielded wire, but it's a mains cable without shield, then you need a filter on this plate so that the current can go to the plate also. So you keep the current from the outside world, you stop them here. So anything going in, it's a current boundary, so everything goes over the boundary. If you go around, yeah, no problem. Like here, if you do it like this, you make a metal plate here with one cable, and the other cable goes there, that means that the noise current will go, if it's a metal case, probably over the outside boundary, hopefully. But if there's any faults or mistakes here in the connection, it might go a shorter way through the inside. So, and then in the end, you want to keep them together anyway, because the current flowing now flow like this, and you want to make this loop small, so you have to bend it together. So why not keep them here together, like this? This is the good one. On the inside it works also. It works both ways. So anything happening inside will be stopped here. So there will be no noise coming out, no noise going in. Ideal. And very simple. Just make the connection. Don't forget it. If you have a plastic box, you can still use the connector plate, like a metal plate, for all connections. I mean, even a plastic television, for instance. You can use a metal plate if you need it on the outside to get all cables on. Okay, this is the practical form of a current boundary. You have a metal plate, which is wide, low impedance. You make sure there's no paint where your connectors go. This is a connector version, no glands. No paint here, so that everything makes good contact. You check the contact, because you cannot see that. You can see a small loop, you cannot see the resistance. So make good contact. Short distance between the connectors, because this current path, if it would be thin, is a common impedance between the inside and the outside. You have to remember. White metal, no paint, and then measure the DC resistance. Because the contact, you have to check. If it makes no contact, you have seen with the experiment, if you don't connect it, it doesn't work. I mean, the ground plane is nice, but if you don't connect it, it doesn't do it. Okay, this is an example of some hybrid form of gland plate. They probably didn't quite understand what they were doing. Here, you have a cable which shows a shield, and I think it's connected here. It's a metal gland. Whether there's paint between, we don't know. We don't know whether this makes contact with this. You cannot see it. At least here, there's a plastic one, so here's no contact because probably there's no shield. But then this plate will not function as a shield because there's a hole in it and there's a cable going through. So it will pick up the current on one side and bring it to the other. So there's a variety of solutions here with plastic, with metal. And, well, actually we measured it and it didn't work. The measuring is usually done at the Thales. From the university we can go with the students to Thales, they have a lab. And lab is millions of euros, so we cannot afford it, but we can go there and show the lab is in and we can measure it. But this was not good. Okay, and then the next thing is, okay, we have protected our equipment with a gland plate or a connector plate, and now we are left with cables, of course. And here is a red cable, which is the noisy one. There's a green cable, which is the sensitive one. And here's a black one, well, we don't know, but it doesn't make noise and it's not sensitive, but it's there. And these three, we give a name or a number. Source, emission, the red, we call it the E cable. The sensitive one is an I cable, the unity. And the three one, this one is a neutral one or indifferent one. So you make a category of cables. In the books you find 5 to 7 categories. You know, extremely noisy, indifferent, sensitive, extremely sensitive, something like that. Depending on the complexity of your system, you can do more or less, but usually 5. These three, if you can separate these three, if you can separate the red one from the green one, then you can do anything. You can separate any category from the other. So I'll allow you the trick, and then you can apply it. This is a model. This is a cabinet with a good protection against common current from outside to inside. So this is a connector plate cabinet. This is the cables. And you see here the loop, the common mode loop, round loop, ambus, created by the cables. The noisy one will create noise and it will flow over the others. So now you have a current loop here. And this noise current flowing over the sensitive cable, but this is the measurement cable for temperature, for instance, or pressure. This is your motor wire with your current controlled circuit with very fast edges. Then you could disturb this cable, and through transfer impedance it will take the current in and you have your noise. To solve it, there's two approaches. Actually, this is one. The one is, okay, we make this loop small. We start with making the loop small. So the neutral goes over there, like this. So now we have two loops. Well, the red one with the neutral and the green one with the neutral. If I make a short circuit there, I have my current boundary. See, it's the same trick. Now you have a noisy loop and a sensitive loop. You can separate them. You can make them small. And that's the trick for cables. Well, the neutral cable, be a mains cable or whatever, you probably would not use a cable for this. You would use some metal for it, which is there anyway. A metal bar or part of the chassis, whatever you have. You can use that to put your noisy cable against the chassis and then connect all cabinets to that same chassis, because the current path has to be there. But you would not use a cable usually. Because if you do that, what you create actually is a new current loop. The noise goes now from the red cable to the black one and it flows in this loop. But it looks like a twin wire. See? These two cables. And two cables would be a twin wire, so it will still emit noise into the outside due to this current. So this is not so good. This is better. White metal with the cable on it. So they call this asymmetric. Small cable, white metal plane is a much better shielding for the cable, let's say, or improvement of the transfer impedance, which you do here, is better with a white metal plate. So usually it looks like this. You put all your equipment